Alright, this is a walkthrough of the extra sheet of paper, the inclined planes worksheet that was given out on Friday in class. And it's a combination of all of the different scenarios that we worked on during class. So we have a pushing force that's pushing up the ramp. We have both static and kinetic incline or friction because we have some sort of rough surface. And we're asked to find the acceleration of the object. So the first two questions talk about when it just starts moving and after a bit of time moving. The key distinction between these is that when it just starts moving, that's going to be using static friction, and then after a bit of time, it will be using kinetic friction. So here, in order to find our static friction, we need to take a look at the equation friction equals mu times normal. So in this case, it is our static friction coefficient times the normal force. And our static coefficient is 0.4. Now we have to find our normal force, and in order to do that, we need to take a look at our free body diagram. So we have our gravity force going directly down, our weight, which is equal to mg, which is equal to 10 times 9.8, or 98 newtons. Then we also have our normal force, which goes up at an angle, which we we'll be able to figure out how much that is in just 1 second. Then we also have going up the ramp our push force of 15 newtons. And if you think about it like this, 15 newtons is not enough to overcome the down the ramp component of gravity. Remember that we can break our gravity components into two components, or gravity vector into two components, a down the ramp or weight parallel and a weight perpendicular component. And so weight perpendicular is going to be equal to mg cosine theta, as per our discussion on Friday, and then weight parallel will be equal to mg sine theta. Okay, so this weight parallel, mg sine theta, is 98 times the sine of our angle, 30 degrees. Sine of 30 is 1/2, so we end up with 49 newtons down the ramp and 84.6 newtons into the ramp. Now, because of then Newton's first law, we know that the F net in our new y direction, and we should remind ourselves that our new y direction goes like this, and our new x direction goes down the ramp like this. Net force in the new y direction must be equal to 0, and so therefore we can say that our normal force minus our weight perpendicular is equal to 0, and that our normal force is equal to our weight perpendicular, which is equal to 84.6 newtons. Now, back to this diagram over here, we can tell then that our friction force must go up the ramp, because down the ramp we have 49 newtons, up the ramp we have 15 newtons, and so our friction force has to go up the ramp like that. So then our normal force is 84.6, and we end up with a friction force of 33.9 newtons. Now we go back over here to the x direction. Here's our y direction, so now we're in the x direction, so net force in the x direction is equal to, it's likely going to accelerate, so we're going to say it's equal to ma. Our down the ramp forces are weight parallel. Our up the ramp forces are our push force and our friction force, and that's going to be equal to mass times acceleration. So we have 49 minus 15 minus 33.9 equals 10 times our acceleration. And so when you go through this, left-hand side ends up being 0.1, and the result is our acceleration is 0.01 meters per second squared, and it's going to accelerate down the ramp. Now the only difference that we're going to have up here, our net force in part B, our net force in the y direction is still going to be equal to 0, which means we can still say that our normal force is equal to 84.6 newtons. We still have the same net force expression in the x direction, which is weight parallel minus our push force minus friction. In this case, though, our friction is our kinetic friction. And so we have to figure out how much that is. So we've got our 15 Newton push force. Our kinetic friction going to be similarly calculated to our static friction. Fk is mu k times the normal force And so we've got 0.2 times 84.6, which is half of this here, so it's going to be 16.95 newtons. And so we're going to have minus 16.95 newtons here, which means we have our result net force in the x direction is 17.05 newtons. And as a result, 17.05 newtons is our net force. That's equal to mass times acceleration. So our acceleration is going to be 1.705 meters per second squared down the ramp. So take a look, understand that as it starts moving, it is moving with a small amount of acceleration, and as it continues to move, it increases its acceleration significantly. So now our next question says, if I push with 1 newton more than is required to get it moving, how much is its acceleration after it begins moving? So this first part, we're talking about 1 newton more than the static friction requires it to push with. And then the second is, after it begins moving, how fast is its acceleration? So the question first is, how much force must we push with to get it moving? Well, we know that without any push force, we have up the ramp 33.9 newtons, and we have down the ramp our 49 newtons. So the minimum push force that we need is equal to 49 newtons minus 33.9 newtons, which ends up being then 15.1 newtons. So then we are going to be pushing with, F push will be equal to 16.1 newtons. And then we're just repeating part B here with 16.1 newtons. So it's 16.1 instead of 15, so we end up then net force in the x direction is weight parallel minus F minus friction kinetic, which is 49 minus 16.1 minus 16.95. So this ends up being then 18.15 newtons. And so we end up with an acceleration then, because this is equal to ma, don't forget. Our mass is 10, so our acceleration then is 1.815 meters per second squared. Okay, 1.815 meters per second squared. And remember, this is down the ramp, so when I ask for how far up the ramp has it moved, you're going to end up with a negative distance. So we're looking for how far up the ramp it has moved in 2 seconds. So our time is 2 seconds. Our acceleration is 1.815 meters per second squared. Our initial velocity is 0 meters per second, and we're looking for final minus initial velocity. And so the result is that the equation we're going to want to end up using is that, I guess our acceleration should be negative 1.815. X final equals x initial plus VOT plus 1/2 AT squared. So we have 0 plus 0 times 2 minus 0.9075 times 2 squared, because 0.9075 is half of our acceleration up here. So we just end up with the negative 3.63 meters. So it actually moves 3.63 meters down the ramp in this problem. And the final question on the first page is, how far vertically has it moved? Well, if we think about it like a mini triangle, if our angle down here is 30 degrees, and we have a distance here of 3.63 meters, we're looking for this side here. We're going to use the sine of 30 is our y direction divided by 3.63. So this side ends up being half of 3.63, or 1.815 meters. So it has fallen 1.815 meters in the first 2 seconds.